All right. Well, let's get started. A bit of an introduction here, and folks can continue to file in. Welcome everyone to this webinar series. I guess this is part 2 of 3. Webinar series called "The Role of Computational Geoscience and Predictive Assessment of Plate Boundary Systems and Hazards." This is put on by the Modeling Collaboratory for Subduction, which is part of a research coordination network aligned with the SC4D initiative. We're happy to highlight here connections between surface and sort of geodynamics, computational issues here. So this is, as I mentioned, part 2 out of 3, and actually the third one is tomorrow. Katie Barnhart from the USGS will be talking, so I encourage everyone to attend. I'll also just highlight here, just reading off the slide, but sort of standard webinar format, I suppose. Ask questions or make comments anytime using the Q&A feature. Gabe Lotto is helping to run logistics here and hopefully facilitate good dialogue. Should also mention that the webinar presentation today will be available on the SC4D MCS website. Link is given there. So if you want to come back and revisit or share, please do so afterwards. My name is Leif Karlstrom. I'm at the University of Oregon, and I'm more or less going to step out of the way here in a second, moderate some questions at the end. But in between, we'll hear a talk by Susanne Buiter, coming to us from Germany, Aachen University. Susanne works on a whole range of problems having to do with continental scale geodynamics. And she's going to talk to us about how coupled tectonics and surface processes shape external plate boundaries. So I guess with that, take it away, Susanne.
Thanks a lot, Leif. I will start to share my screen again.
Yep, stop here.
I can just boot you off, I can see that. Okay. So I hope that's clear for everyone, and I hope you can hear me well. And thank you for joining. So I love the concept of these joint thematic webinars between the organizations of the abbreviations. And I'm looking forward to discussing links between tectonics and surface processes. So I have the Q&A window open, so if you'd like to type questions already when I'm talking, so please go ahead. So as you can see from the title, I will be looking into the interplay of surface processes and extensional tectonics. But before I do that, I would like to take a brief look at the feedbacks between surface processes and shortening tectonics. And the reason for that is that much of our understanding of feedback relations between tectonics and surface process has come from mountain building settings. So if we look at this world map of erosion rates from Hergarten and Kenkman, we can immediately see that there is a relationship between high topography and erosion rates. So high areas of topography, like for example the Cordillera in North America, South America, the Himalayas, they tend to have high erosion rates. So high topography focuses erosion, and it's kind of what we intuitively expect, right? So mountains, they catch the rain, they're often glaciated, so they will be eroded faster than flat-lying areas would. But in turn, erosion would impact the mountain building process. So erosion causes tectonic deformation and exhumation. And there have been analog and numerical models investigating that since at least the early 1990s, if not before. And I show you here 2 examples. On the lower left is an early model from Jean Willett from 93, where the wind carrying rain comes in from the left. You can think of that as coming in from the west on the west coast of the South Island of New Zealand, for example. And that focuses the erosion on the left side of this little origin, causing a large amount of deformation and exhumation on the left side of that origin is visualized by this ghost grid above the surface. The analog model of cruise, you see the no erosion example on the top, the one with erosion below, and it shows how erosion can focus deformation and cause large offset on the thrusts in the system. And you can think of that as a critical wedge. Right? The system could be happy and stable, but then when material is removed, it deforms to reach the stable field again. So of course our models have become more fancy since these models from the 90s, but the main conclusion is the same. So in shortening settings, we're finding a positive feedback between erosion and tectonics. So the processes enhance each other. And you could think of that as that erosion is a tectonic weakening process. So what do I mean by that? Surface erosion causes a decrease in vertical stress in the materials below, and therefore a decrease in the brittle crustal strength. So if you think about a crustal block here in the orange and yellow, if it's in shortening, the main principal stress sigma 1 is horizontal, the overburden stress sigma 3 is vertical. And if I put the block at failure, you would get the Moore diagram like here. So sigma 1 here in the space of shear stress versus normal stress. If I remove material, I'm reducing the overburden stress, so my Moore circle moves towards the left. And you can see that you now need less differential stress to bring the model to bring the material to failure. So it has become, it's easier to fail, so it has become weaker in a tectonic sense. So erosion is weakening in shortening, and sedimentation is brittle strengthening. The role of erosion in models has been studied a lot. Sedimentation probably a bit less, which probably has to do with the high mountain setting. You would expect more erosion than you would probably expect sedimentation. But in extensional problems, of course, sedimentation plays a big role. And in fact, when we look at offshore sediments, we can see that there can be substantial thickness of sediments. This is the global sediment map from Straumetal, and in the sort of deep brownish colors here, you would have thicknesses of about 5 kilometers. And as the colors become lighter, the package becomes thicker. And you can see the enormous thickness of sediments that are present at some of these continental margins, like around the Atlantic system. And you can also see regional variations in the sediment thickness. Now one thing, when you look at the sediment package, is that we do not really know when during any extension process this was deposited. So whether these sediments were already there before rifting started, or deposited during rifting or after. So it's just to make you aware that that's when we look at the map like this, it's a big pack of sediments, but it doesn't say if it was before, during, or after rifting. In my presentation, I'm going to focus on sediments that were deposited during rifting, so syn-rift sediments. I'm not going to worry about anything that was present before or that's happening after. So when you look at examples of rifted continental margins, 2 things stand out, at least for me. So one is that the shape of the margins can be quite different, and shape in terms of width as measured from, say, fairly undisturbed continent towards the ocean. It can be narrow or wide, and the amount of sediments can be different, as we already saw on the map on the previous slide. So on the left column, I've plotted narrow margins with examples from North Norway, the Goulburn Spur offshore the UK, Flemish Cap offshore Newfoundland. On the right are wide margins, where you have a very wide region, a long transition from continent to the ocean, like mid-Norway and the North Namibia and Angola margins of West Africa. Now in yellow are sediment layers. And what you can see is that the narrow margins tend to have little sediments, but the wide margins have thick packages of sediments. And of course, I've chosen examples that really strongly highlight this, but this seems to be, at least from what I have seen, a correlation that occurs on more margins. So the thing is, it doesn't have to be a causal relationship, right? So the fact that the wide margins have more sediments and the narrow margins have little sediments doesn't mean that there has to be a link between them, but it did make me wonder if there was a link between rifting and sedimentation. And that, of course, first brings up the question, what in the first place controls the shape of continental rifted margins? Why are some margins narrow and other margins are more wide? And can surface processes play a controlling role in determining this architecture? And of course, I'm going to argue that sedimentation and erosion are important, but I hope that I can convince you of the importance of the role of surface processes. Now, numerical modelers think that they've got a pretty good handle on what makes margins narrow and wide. And as a numerical modeler, I agree with this, but I will step you through this. On the left column are some examples of models that create narrow margins, so a sharp transition from continent to the ocean. And these are formed for initial rheologies of the continent that are what we call normal to fairly strong. Whereas on the right margin, or the right column, we have examples where the margin is wide. So there's a wide region where the crust is very thin, also called hyperextended. And in these cases, the initial lower crust is weak and usually extension velocity is a bit higher. Now, and what you can see is here there are examples from different modeling groups using different codes. And we're seeing, I mean, small differences, but overall we're seeing the same style, so that's really reassuring. So I would like to first explain you how we actually get to this. So how do we create the narrow margin and the wide margin? And then come to why I think that there is still an issue with our story of creating narrow and wide margins, and that this is not the complete story. So I will first need to step you through some of the details in my numerical model setup. So I will show you models that are initially 240 kilometers deep and 800 kilometers wide. So they consist of a crust in orangey and yellow that's 40 kilometers deep initially. And the 40 kilometers is based on a global compilation of crystalline and Mooney. And initially the MOHO temperature is about 600 degrees centigrade. The lithosphere is at 120 kilometers, initially at 1300 degrees centigrade, and these are all very standard values. My models are in a way idealized, so they're laterally homogeneous. I'm ignoring inheritance, fluids, melts, and anything that would make it more complicated. Now the materials are either brittle, meaning they can break, or they're viscous, meaning they can flow. So the effective stress versus depth shows the maximum effective stress that the materials can sustain before they deform. And what you can see is that parts of the base of the lower crust and base of the upper crust and most of the mantle will behave viscous, so they can flow, and parts behave brittle in these straight lines. Now for the viscous parts, I used scaled up floor laws from Gleason and Tallis, Rybak, Andreessen, and Huff and Costa. The brittle part is a smooth Moore-Coulomb, it's a Drucker-Prager model. And I assume that the materials weaken with accumulated strain with a factor of 2, and that's based on microphysical models of Bos and Spires. Yeah. Now my models are Eulerian, so it's a fixed grid. You can think of it as an aquarium where I'm pulling materials out. I will need to balance that inflow so I don't get surface movements just because I'm moving material in or out. And I achieve extension by pulling on the sides of the lithosphere. And my extension rates, the full rates, so both sides added, are 0.5 centimeter to 4 centimeters a year. Now, up to about 2 centimeters a year is probably representative for continental extension. Faster would be more going towards oceanic rates. Yeah, that's probably that. Then to focus my first information in the middle of the model, I put a small C just below the MOHO in the strong brittle part. And that makes sure deformation starts here and not somewhere at the sides. And then I solve inside my box for velocity, pressure, and temperature. Now I do that using a finite element software called Shulac, which I've been developing with my colleague Susanne Buiter from Geoscience in New Zealand. It's an arbitrary Lagrangian Eulerian code, so we have the Eulerian grid where we solve the equations, but it can deform slightly in the vertical direction. And in that way we have a free surface, and that also allows us to remove material, so erode, or add material, so do sedimentation. Some other features are that we track material properties through the grid using tracers. Use Paradiso Solver, the code is standalone. We try to have a version that is not depending on any commercial software. It's of course benchmarked. And on the scale of Greg Tucker of the seminar of yesterday, between build the code as needed, set it aside when done, versus share and maintain community software, I guess like many of softwares that people develop, we're somewhere in between, but maybe a bit more towards the first than to the second. So our code is documented, but we do share with collaborators, but we certainly are not putting it out there. And we don't have a help desk, and we don't have a user manual, and we tend to branch off into versions. So that's why I would say maybe a bit more towards the first than to the second. So if I take that setup that I was just describing, and I use standard rheology, like I was showing you, so normal, and extend it 1 centimeter a year, then this is what you get. After about 17 million years, we get breakup of both crust and lithosphere. The system is very symmetric, and there is a sharp taper, so it's a sharp transition from continent to the ocean. So this explains the models in the first column that I was showing you. We get a narrow transition from continent towards the ocean. Now I was arguing that if we make the lower crust weak, we would get wide margins, and I will show you that. So to make my lower crust weak, I just make it weak in a lithological sense. I divide the viscous strength by a factor of 5. And on the next, I'm going to show you a movie. So it will show the crust in the orange and yellow, the lithospheric mantle in the blue, asthenosphere in the light blue. And on top of that, you will see the computed velocities. We'll trace the 600 and 1300 degrees isotherms, and then there's a zoom to topography and to surface heat flow. So initially, I should move my mouse, right? The model is initially quite symmetric, but then you can see how the center of extension is moving here towards the left. And it's kind of peeling material away from the left margin and transferring that to the right margin. And you can see here this wide region that's forming of thin continental crust. And then we get breakup here. So now we have created a system where we have a narrow margin on the left, and we have a wide margin on the right. You can see the 1300 degrees isotherm is kind of the base of the lithosphere of the ocean. We create a topographic basin that is a few kilometers steep, as you would expect. And you can see in the surface heat flow how this material, as it moves away, how it cools with time. So the crust itself is still behaving brittle. And the interesting aspect is that we have now created this asymmetric system, which agrees with what other modelers found. But what is actually happening? Why is this system that initially is so symmetric? Why is that going into this asymmetric mode? Now Sascha Brun, in his 2014 paper, put forward an explanation that I would agree with, and as I observed the same in my model. So this is from his paper. What you see here is the viscosity field. The blue colors are strong materials. The red, yellow, greenish colors are more weak. The figure looks the same as the one I've just shown you. Breakup, future breakup is here. So there's a narrow margin and a wide margin. And what Sascha argues is that what we're seeing here is lateral migration of the rift. So it starts in the center, it migrates towards one side of the system. And while it's doing that, it's transferring material from this one margin to the other. And as you can show in the cartoon here, to allow that material transfer to occur, the crust in the continent needs to be able to flow, to allow the material to move. And one way in which it can flow is if it has a low viscosity. And viscosity can be low if it's warm. So then it's weak in a viscous sense. And we can make it initially weak, but we have to keep it weak. And we can do that in an extending system by bringing up hot mantle material. So we're advecting heat up. And we need to advect the heat up faster than the system cools from above. So that means that we cannot be extending too slow, because if we're extending slow, we're dominated by cooling, and this lateral rift migration mode cannot be triggered. So your thermal Péclet number needs to be larger than 1. You need to advect heat fast enough to keep the lower crust of your continent weak enough that it can flow and accommodate this transfer of material. But there is an issue with this. So I've now shown you these two modes. One, we can create the narrow margins, we can create wide margins. But the issue is that for most of our extension velocities and for most of the rheologies, we get a narrow tapered margin, so a sharp transition from continent to the ocean. And I show you that here in this matrix. So the top models have a weak lower crust initially. This is what I call standard, and here I've made the crust strong. And then for different extension velocities, 0.5 centimeter, 1 centimeter, 2 centimeters. And you can see for most combinations, I create a sharp transition from continent to the ocean. And only if I have a weak lower crust and I extend at higher velocity, can I create this wide margin. So that is a bit of an issue. So it seems that the numerical models point out that we're only creating these wide drifted margins for special circumstances. But in nature, we actually observe these wide drifted margins quite often. So this indicates that we're missing something. And obviously, I'm going to argue that what we miss are the surface processes. So what are the effects of erosion and sedimentation on the extension system? And this is, of course, my modeler's perspective. So there's a mechanical response. There's an isostatic response where we deposit materials, more will move down, and where we remove materials, more will move up. And these vertical movements can induce lateral flow of viscous layers in response. But in addition to the mechanical response, we have a rheological response. I already was arguing that erosion in shortening systems is a weakening process. I will argue that it's also weakening in extension, and that similarly, sedimentation is strengthening in extensional systems. But there is an opposite effect, and that is that if your sediments have a lower thermal conductivity, they can trap heat in the part below, because the heat cannot conduct away so fast. That means that materials below can stay warm, and they will stay weak in a viscous sense. And I will go a bit deeper in these 2 points on the effects of surface processes on rheology in an extensional system. So this is similar to what I was showing before. But now for an extensional system. So now the largest compressional stress, sigma 1, is the overburden stress and is vertical. I've put the arrows the wrong way around, but I've again put the block in extension, so it should be a normal fault here, sorry for that. And what I'm arguing is that surface sedimentation is strengthening. It increases vertical stress and therefore it increases brittle strength. So if I have a block here that's at the verge of failure, with my sigma 1, sigma 3 in more space, if I add sediments, I'm increasing my sigma 1 and my Mohr circle will shift towards the right. And that means that I need larger differential stress to bring the material to failure. So sedimentation, the adding of material, has the effect to make the crust underneath stronger in a brittle sense. But opposing that is an effect where sedimentation can make the crust underneath weak in a viscous sense. And I'll illustrate that with 2 simple rift models. So what I have here is a crust in these purplish colors, lithospheric mantle in blue. I'm creating a symmetric rift basin and I'm filling it completely with these yellow and red sediments. And then I'm letting the model sit for 100 million years while it's trying to reach thermal equilibrium. Now, if the thermal conductivity of sediments and crust is equal, then indeed the model reaches thermal equilibrium. You can see the isotherms, and if anything at all, then maybe the model here is even a bit cooler because we have less crust, less heat-producing elements below the basin because of the thinning. But if the thermal conductivity of the sediments is lower, heat cannot conduct away so fast. And then after 100 million years, you can see still the elevated isotherms beneath the basin. So that means that the lower crust beneath the basin has higher temperature than the adjacent crust, and it will be therefore weaker in a viscous sense. So when during extension we have erosion and sedimentation, we have these different processes. From the brittle perspective, erosion is weakening, sedimentation is strengthening. But from the viscous perspective, sedimentation is weakening. So we have these, in a way, opposing effects of sedimentation. And we do not know in advance which of these is going to be the important one, which of course is why it's so useful for us to do numerical models. Right? So I'm going to show you a series of experiments next, where I'm going to vary crustal rheology, and that is because I've just been arguing that surface processes act on crustal rheology. I'm also going to vary the extension velocity because that also affects the rheology, and I'm going to have models without surface processes and ones that are with. Now for the surface process model, I'm going to use a very simple one that's just depending on slope with a coefficient, a slope erosion coefficient K. I just put up some remarks and thoughts and questions that I have regarding the slope surface, the surface process model that I'm using. I'm not necessarily going to answer them, but so one way in which the way in which we implement the surface processes is because the models have a true free surface. So we remove material in erosion, we add material in sedimentation, and we shrink or we stretch our Eulerian grid on which we solve our equations to accommodate the surface processes. Now, as I said, I'm using quite a simple surface processes model. I could have used others, I could have made it more complicated. Whether it matters, I cannot really tell you. And in fact, I have seen very few comparisons where people take the same tectonic model, but they then run different surface processes model across it for a direct comparison. Now, one thing in my models is that I'm stepping through with quite large time steps, Courant steps that are determined based on cell size and velocity. And that will imply an averaging. So if anything in the surface processes model is occurring on a short time scale, I'm averaging that out. So for example, if there's slumping, this will have to be averaged because my smallest time step is 2000 years. If anything in the surface process model is also being very fast, that this can lead to numerical stabilities issue at your surface for this free surface process model as well. And then one thing to keep in mind is that there is a time delay between when your tectonics starts up and your surface processes start to play a role. And that's because you first need to create subsidence for sediments to be deposited, or you need to create an uplift for erosion to occur. So that means that your tectonics is already starting and it's setting up a style of deformation before your surface processes start to act. And that's something to keep in mind, that surface processes in many cases will start to come in later. Okay, so what I will show you is 3 end snapshots of a model. Time is at the bottom right. I'm focusing in on the crust. In the left column will each time be the 3 models without surface processes. For a weak lower crust, standard lower crust, strong lower crust. And I show you here in the strength profiles what I mean with that. So even in the strong model, there is still a little bit of potential viscous behavior at the base of the lower crust. I first start with a low extension velocity, 0.5 centimeter here. And then on the right column, I will show you the same models, but then with surface processes added. You can see the sediments in these brownish colors. Now you can see that at 0.5 centimeter here, I mean, we do see the rift flanks being eroded. We can see the sediments deposited, but if you look from a bit back and you focus on the crust, you can see that there's not much difference in the style of deformation of the models. And that actually is still the same for 1 centimeter here. Not much is happening. But if I extend a bit faster, we now get the model that I was showing you before, where for a weak lower crust at 2 centimeters a year, we get this, the wide margin. You can see for standard lower crust, the model breaks up, but we can see a subtle change here for the model with surface processes. It still breaks up. But at higher extension velocities, we see a mode switch. So the model that breaks up for the standard lower crust without surface processes, if I add sediments, it now develops a wide margin. And what I argue is happening is that the sediments that are being deposited here, so which come in quite late in the process, they strengthen the crust enough that they suppress the breakup. And I will show you these two models again, but now at the same stage, about 4 million years. So the one without surface process, the one with. So what's happening? Remember that I was arguing that we can get this lateral rift migration that causes a wide margin to form if the lower crust of the continent is weak enough to allow a flow, to allow transfer of material from one margin to the other. And you can see that in the model without surface processes here, there's indeed a tendency in the viscosity plot here of low viscosity values. I should say that this is a logarithmic plot of viscosity where the reddish colors are low viscosity, bluish colors are high viscosity. And you can see that in the continental crust of the model without surface process, there indeed the lower crust of the continent has low viscosity, but before this lateral rift migration mode can actually start, the crust breaks up. But if we add sediments, they suppress this early breakup and they allow then this rift migration mode to develop. And so I would argue that even though sedimentation starts to play later in the process, they play a crucial role. They suppress the early breakup. And I would say it's the brittle strengthening effect that is therefore dominant in this process. And I can make this a little bit more quantitative. So what I plot here, every dot is a model result. On the vertical axis is the initial strength of the lower crust. It's weak below here, it's stronger up here. On the horizontal axis is the Péclin number. And where the Péclin number is smaller than 1, the model is dominated by conduction. So heat will conduct away, it will cool, and we would never get this lateral rift migration mode. The Péclin number is highly dependent on velocity. So you can also see that this horizontal axis is my extension velocity increasing towards the right. Now the black dots, the majority, are all the models that created a narrow margin, sharp transition from continent to the ocean. The red dots, which I've highlighted in the yellow field, are the ones that created a wide margin. And this is for the models without surface processes. And it illustrates what I was arguing before, that the standard seems to be narrow margins, and only for a specific set of parameters, the initial strength of the lower crust and extension velocity, we can create this wide margin. But if I include surface processes, and then it's mainly the sedimentation, I can increase the model space over which wide margins form. What I argue, my proposal, I should say, what is happening is that the sediments that come in, they suppress the breakup, early breakup of the crust through their brittle strengthening effect. And they just allow the margin to go into a mode of lateral rift migration to create this wide continental margin. So these were the questions I was asking in the beginning. So what controls the shape, and can surface processes influence crustal architecture? Now, what controls the shape? From my experiments, I see that a standard behavior seems to be to create sharply tapered margins, so sharp transition from continent to the ocean for most of the values of extension velocity and lower crustal strength. And that we only form wide margins for relatively high extension rates, above 2 centimeters a year is high for continental extension, and for a lower crust that's initially weak. And of course, seen from observation side, this is a bit problematic because we observe wide rifted margins quite often. And then I would argue that we can create wide rifted margins in more cases by including surface processes and then mainly sedimentation. And that these surface processes can play an important controlling role in continental breakup. And what happens is that the sediments that are deposited on the extending continental crust, they suppress the breakup because of their brittle strengthening effect. They then allow lateral rift migration to occur and a wide margin to form. So a margin that would initially break up early and create a narrow margin is instead experiences a switch in deformation modes and becomes a wide margin instead. And that mode transition depends on extension velocity, the crust rheology, and of course on the amount of sediments. But what it shows is the importance of surface processes, and that when we look into extension, we should be taking into account the effects of sedimentation, probably also of erosion, similarly as we do for shortening problems. So if I could choose and people would give me lots of time, what would I like to do next? What would be ways to look into the interaction between surface processes and tectonics? One thing that I would like to do is to take the same tectonic model and to run different types of surface processes in collaboration with people who actually know something about surface processes, and to see if that plays a role at all and what the differences would be. I'm also interested in the question on at what time during the process do surface process and tectonics start to interact. And this has to do with what I was saying earlier. You need to create topography before erosion starts. You need to have subsidence before you can have deposition. And in my models, I was showing that even though sedimentation comes in late for the rifted margins, it can still switch the style. The model that would be narrow, a narrow margin becomes a wide margin, even though the sediments come in fairly late. But maybe there are also systems where the tectonic deformation style is already set quite early. And erosion sedimentation doesn't really matter anymore. And how does this work in shortening? And what are the effects of any time averaging that occurs between the surface process model and my tectonic model? And another thing is the models I've showed you are very idealized. So they have these initially flat-lying, laterally homogeneous layers. And I'm not considering inheritance, no fluids, no melts. But what happens for surface process for models that are less idealized? Are there maybe some feedback effects that I have not considered at all? So that was my story, and I would be happy for any questions or any suggestions or disagreements on what I've been telling you.
Wonderful. Thank you, Susanne. Great thought-provoking talk. I guess we're going to open this up to discussion and questions. As mentioned at the beginning, prefer you to use the Q&A feature here. So if you
shall I leave the slide up or shall I just stop sharing?
Oh, I guess that's up to you.
I can always reshare.
Yeah. Let's see. Okay, great. So we have one coming in here from Joyce Sim. Kind of a technical question: is the mesh symmetric? Can the numerical methods used lead to asymmetry?
Yeah, that's a nice question. The mesh is symmetric in the sense that you could mirror it left or right. But it's not symmetric in the vertical sense. So I have a mesh refinement in the crust and the lithosphere, and the mesh becomes coarser further down. But it's always the same in the lateral sense. But the asymmetry is of course the really interesting one, right? And sometimes we see it become asymmetric with breakup on the left margin, and sometimes the model is mirrored and it's on the right margin. What I think allows the asymmetry to develop is in the brittle part in the plasticity. in the strain weakening that I've implemented, because that is a non-linear effect in the system. So the system will want to become asymmetric, but it will go left or right. Where it will go is decided by an element that is numerically a little bit more strained. So it will then start to strain soften plastically. That part becomes numerically a little bit weaker and has a feedback effect, and it will go that way. So I hope that answers your question, Joyce.
Great. Maybe just as a quick follow-up, just because I'm curious, is this the type of thing that is grid resolution dependent? Could you see a different asymmetry forming, right, for different mesh?
No, but we do see dependence of, for example, the dip angle of shear bands on resolution. So you need a fairly fine resolution to get outer angles or more column angles. And in the models that I presented, they're fairly coarse, so many shear bands would initially be at 45 degrees. Of course, I mean, not coarse on the scale of the model, but if you would look in detail at the crust.
Great. Okay, we have a bunch of questions. This is great. So the next one, and I apologize in advance for butchering everyone's names. So this is, yeah, from Renat Hartog, great talk. How would extruded materials come into play? Is this implicitly part of your model, or could you add it?
And hi, Renata. So they're not part. But say if you would have if it's extruded, do you mean magmatic materials? So
let's see. Yes.
Yes. Okay. Yeah. So yeah, we can, and we've done this. We can add melting, for example. But the thing is that for rifted margins, the melts come in quite late if you just do it by decompression melting. If you would have an external melt source like a nearby plume impacting, then of course that has a huge effect on your rheology, so a weakening effect. So I think that would be quite interesting to see if you would be viscously weakening it, how that then plays into the strengthening effect of any sediments that you put up. I would expect if you put in a plume, the plume wins and it breaks up.